Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 144, binary tree preorder traversal. This problem is a fundamental exercise in tree traversal algorithms, where we'll explore how to visit nodes in a specific order: current node, left subtree, and right subtree. Let's dive in and break it down step by step. In this problem, we are tasked with performing a preorder traversal of a binary tree. Preorder traversal is a depth-first traversal method where we visit the nodes in a specific order. First, we visit the current node, then traverse the left subtree recursively, and finally, traverse the right subtree recursively. The input to our function is the root node of the binary tree, which might be empty. The output is expected to be a list of integers that represents the values of the nodes visited during the preorder traversal. To better understand this, let's look at a few examples. Consider the first example. The input is a binary tree represented as an array 1, null, 2, 3. Visually, this tree looks like this. The root node is 1, which has no left child but has a right child, 2. Node 2 then has a left child, 3. To perform a preorder traversal, we start at the root node, 1, and add its value to the result. Then, we move to the right child, 2, adding its value. Finally, we traverse the left child of 2, which is node 3, and add its value to the result. This gives us the final output of 1, 2, 3. In the second example, we are given an empty tree, represented by root equals. Since the tree has no nodes, there are no values to traverse, and the output is simply an empty list. This highlights that the solution must handle cases where the input tree is completely empty, returning an appropriate result. In the third example, we have a single node tree where the root is 1. Represented visually, the tree consists of just the node 1. Since there is only one node, the preorder traversal visits this node and adds its value to the result. The output in this case is 1. These examples help illustrate how preorder traversal works for different tree structures. The problem also specifies some constraints and edge cases to consider, such as handling large trees with up to 10,000 nodes, ensuring the traversal respects the preorder rules for skew trees, and efficiently processing trees with values in the range of -100 to 100. To tackle the problem of binary tree preorder traversal, we need to traverse the tree in the order of visiting the current node first, followed by its left subtree, and then its right subtree. One intuitive approach is to use recursion. This leverages the natural hierarchical structure of a binary tree. The steps are straightforward. If the current node is null, we stop the process. Otherwise, we add the value of the current node to our result list, then recursively traverse the left subtree, and finally the right subtree. The time complexity here is O(n), since every node is visited once, and the space complexity is O(h), where h is the height of the tree. For a balanced tree, this would be O log n, but for a skewed tree, this could degrade to O(n). This makes recursion both efficient and elegant, but we must consider its limitations, especially when the tree depth is large. While recursion is simple and intuitive, it does introduce the risk of stack overflow with very deep trees. To mitigate this, we can turn to an iterative approach using an explicit stack. This approach mirrors the recursive process but avoids the limitations of the call stack. The steps involve starting with an empty stack and pushing the root node. As long as the stack isn't empty, we pop a node, process its value by adding it to the result list, then push its right child, followed by its left child, onto the stack, ensuring that the left child is processed before the right. The time complexity remains O(n), as we visit each node once, and the space complexity stays at O(h), determined by the maximum number of nodes held in the stack at any time. This strategy is robust and eliminates recursion depth concerns, though it's slightly more complex to write compared to recursion. The iterative method improves memory handling for deep trees, but we can go even further with Morris traversal, which achieves constant space usage. This approach modifies the tree temporarily to facilitate traversal. The idea is to use the tree's structure by creating threads from nodes to their in-order predecessors. Starting at the root, if a node has no left child, we process it and move to its right. Otherwise, we find its rightmost node in the left subtree. If this rightmost node hasn't been threaded, we create a temporary connection back to the current node and move left. If the thread already exists, we remove it, process the current node, and move right. This method ensures that we traverse the tree without using extra space, visiting each node twice, once to create the thread and once to process it. While its time complexity is O(n), its space complexity is O(1), making it highly efficient in terms of memory usage. Morris traversal achieves optimal space usage, but it comes with trade-offs. Temporarily modifying the tree structure may not be acceptable in all scenarios, and the method is more complex to implement and understand. Considering these factors, the iterative approach using a stack emerges as the preferred strategy for this problem. It strikes an excellent balance between simplicity and efficiency. Recursion, while elegant, risks stack overflow for deep trees, which makes it less reliable. On the other hand, Morris traversal, though space-optimal, is unnecessarily intricate for this problem, where minimizing space isn't a critical requirement. The iterative approach avoids recursion limits while remaining straightforward and efficient, making it a practical choice for a wide range of tree structures. When comparing the three methods, recursion stands out for its simplicity but is risky for deeply nested trees. The iterative approach, which we've chosen, is robust and handles all tree depths safely, with moderate complexity. Morris traversal offers the best space efficiency but sacrifices simplicity and temporarily alters the tree structure, which may not always be desirable. By selecting the iterative stack-based approach, we achieve a solution that balances safety, efficiency, and ease of implementation. This approach is practical, avoids recursion depth issues, and remains clear to understand, making it the ideal choice for solving this problem. The problem we're tackling is to perform a preorder traversal on a binary tree. In preorder traversal, the order of visiting nodes is critical. We first visit the current node, then recursively traverse the left subtree, and finally the right subtree. The goal is to return a list containing the values of all nodes in this specific order. To solve this, we can use a recursive approach that takes advantage of the binary tree's hierarchical structure. First, we define a helper function called preorder node that will handle the traversal for each node. This function is designed to work recursively, breaking the problem into smaller parts. The recursion is controlled by a base case, which ensures that if the current node is null, the function stops immediately. This prevents unnecessary processing and ensures we don't attempt to traverse beyond the tree's boundaries when we reach a leaf node's child. Once we ensure the base case is handled, the next step is to visit the current node. This is the main action of the preorder traversal. We append the value of the current node to a result list. This step happens before exploring any of the subtrees, which is why it adheres to the preorder rule. After processing the current node, we move to the left subtree by making a recursive call to preorder node.left. This ensures that all nodes in the left subtree are processed before moving on to the right subtree. Finally, we handle the right subtree by calling preorder node.right. Once both subtrees are processed, the traversal is complete for the current branch of the tree, and the function continues to unwind until the initial call is resolved. At the end, the result list, which now contains all node values in preorder sequence, is returned. The accompanying Python code demonstrates this process step by step, showing how each phase of the algorithm is implemented in the recursive function. The final line of the code snippet initiates the traversal by calling preorder root, starting the recursion from the root of the tree. This ensures that the algorithm begins processing from the topmost node and traverses the entire tree. There are several key insights to note here. First, the recursive nature of binary trees aligns perfectly with the recursive solution, as each subtree is itself a binary tree. This makes recursion an intuitive and elegant approach for traversal problems. Second, the order of operations, visiting the node first, followed by the left subtree and then the right subtree, ensures that the traversal adheres strictly to the preorder sequence. The placement of the result.append step in the code guarantees this order. Finally, the base case, where the function exits if the current node is null, is crucial for preventing errors and ensuring that the recursion terminates appropriately when there are no more nodes to process. Now let's discuss the data structures and complexity involved in this algorithm. The result list is central to the traversal, as it stores the values of nodes in the correct order. This list is updated in place during the recursive calls, which means no additional data structure is needed for the output. Another key component is the call stack, which the recursion implicitly uses to keep track of function calls. This eliminates the need for an explicit stack structure, as the system manages it for us. In terms of complexity, the time complexity is O(n), where n is the total number of nodes in the tree. This is because each node is visited exactly once during the traversal. The space complexity is O(h), where h represents the height of the tree. This is due to the recursive call stack, which, in the worst case of a skewed tree, could grow to n levels. In the best case of a balanced tree, the space complexity reduces to O log n, making the approach efficient for most practical scenarios. Finally, let's consider some edge cases and potential optimizations. For an empty tree, where the root is null, the function should return an empty list, as there are no nodes to traverse. In the case of a single node tree, the result should simply be a list containing the value of that one node. For trees that are completely skewed to the left or right, the algorithm still produces the correct traversal order, though the recursion depth reaches its maximum in these scenarios. While the recursive approach is intuitive and works well for most balanced trees, it can lead to stack overflow for very deep trees. To address this, an iterative approach using an explicit stack can be employed. This avoids reliance on the system's call stack and provides a more robust solution for extremely large or unbalanced trees. However, for typical cases, the recursive method remains straightforward, efficient, and easy to implement. This solution implements the recursive approach for binary tree preorder traversal. The treenode class defines the structure of a binary tree node, with a value, val, and pointers to left and right children, left and right. Within the solution class, the preorder traversal function starts by initializing an empty list called result to store the preorder sequence. The nested traverse function handles the recursive traversal of the tree. The traverse function takes a node as input. If the node is none, it returns immediately, base case of recursion. Otherwise, it appends the value of the current node, node.val, to the result list, ensuring that the current node is visited first. Then, it recursively calls itself on the left child, node.left, to process the left subtree, followed by the right child, node.right, for the right subtree. Finally, the traverse function is called with the root of the tree as its starting point. After traversal is complete, the result list, now containing the preorder sequence, is returned as the output. This code ensures that all edge cases, including an empty tree, are handled properly. Here, we begin by defining the structure of a binary tree node using the treenode class. Each node has a value, as well as references to its left and right child nodes. The class includes three constructors, one default constructor, another that initializes only the value of the node, and a third that initializes the value along with its left and right children. Next, we create the solution class, where the preorder traversal method is defined. This method takes the root of the binary tree as input and returns a list of integers representing the preorder traversal of the tree. Inside the method, we initialize an empty list called result, which will store the traversal output. To populate this list, we call a helper method named traverse, passing the root node and the result list as arguments. Finally, the result list is returned, which will contain the values of the nodes in preorder sequence. The traverse method is implemented as a private helper function to handle the recursive traversal of the tree. It takes the current node and the result list as input. The first step is a base case. If the current node is null, we simply return, as there are no further nodes to process. Otherwise, we add the value of the current node to the result list, marking it as visited. Next, we recursively call the traverse method on the left child of the current node to process the left subtree. Once the left subtree is fully traversed, we make another recursive call to the right child to process the right subtree. This ensures that the nodes are visited in the correct preorder sequence, first the current node, then the left subtree, and finally the right subtree. To begin with, let's look at example 1, which involves a simple binary tree. The tree has a root node with the value 1, a right child with the value 2, and a left child of node 2 with the value 3. Starting at the root, we append the value 1 to our result list, so the result is now 1. Since node 1 has no left child, we skip the left subtree and proceed to its right child, node 2. We append 2 to the result, making it 1, 2. Next, we move to the left child of node 2, which is node 3, and append its value to the result. Now the result is 1, 2, 3. Finally, since node 3 has no children, we finish the traversal. The final output for this example is 1, 2, 3. Now in example 2, we have a complete binary tree. The root node is 1, with left and right children 2 and 3, respectively. Node 2 also has 2 children, 4 on the left and 5 on the right. Starting at the root, we append 1 to the result, so it becomes 1. We then move to the left child of node 1, which is node 2, and append its value to the result, making it 1, 2. From there, we traverse the left subtree of node 2, reaching node 4. We append 4 to the result, so the result is now 1, 2, 4. Since node 4 has no children, we return to node 2 and explore its right subtree, which leads us to node 5. We append 5 to the result, giving us 1, 2, 4, 5. After visiting node 5, we find that it has no children, so we return to the root node 1 and traverse its right subtree. This brings us to node 3, where we append its value to the result, making it 1, 2, 4, 5, 3. Finally, since node 3 has no left or right children, the traversal is complete. The final output for this example is 1, 2, 4, 5, 3. Additionally, let's consider example 3, which is a single node tree with just a root node, 1. Starting at the root, we append its value to the result, so the result becomes 1. Since the root has no children, the traversal ends here. The final output for this example is 1. To summarize, the preorder traversal follows a simple and consistent process for each node in the tree. First, we visit the node and add its value to the result list. Next, we traverse the left subtree by recursively calling the traversal function on the left child. Finally, we traverse the right subtree in the same way, ensuring that the nodes are visited in the order root, left, and then right. This systematic approach applies to binary trees of all shapes and sizes, making it a reliable method for preorder traversal. The time complexity of the recursive solution for binary tree preorder traversal is O(n), where n is the total number of nodes in the tree. This is because the algorithm visits each node exactly once during the traversal process. Let's break this down further. First, for every node, the algorithm performs a constant time operation to append the value of the node to the result list, which takes O(1). Additionally, the algorithm makes 2 recursive calls for each node, one for the left child and one for the right child. The total number of these recursive calls is proportional to the number of nodes in the tree, which is n. Since the overall work done is directly proportional to the number of nodes visited, the total time complexity of the algorithm is O(n). Now, let's analyze the space complexity of the algorithm, which is O(h), where h represents the height of the binary tree. This comes from the stack space required for the recursive function calls. The depth of recursion depends on the height of the tree. For a balanced binary tree, the height is approximately log n, resulting in a space complexity of O log n. On the other hand, in the worst case of a completely skewed tree, where all nodes are either to the left or to the right, the height of the tree becomes n, and the space complexity increases to O(n). Additionally, the result list requires O(n) space to store the values of all n nodes, but since this space is necessary for any implementation, we focus on the extra space used by the recursion stack. Therefore, the overall space complexity is determined by the tree's height and is O(h). Let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, the tree is perfectly balanced, and the height of the tree is log n. This means the space complexity for the recursion stack is O log n. In the worst case, the tree is completely skewed, and the height of the tree is n, leading to a space complexity of O(n). Importantly, the time complexity remains O(n) in all scenarios because every node is still visited exactly once, regardless of the tree's structure. Comparing this recursive approach to others, such as a naive traversal using an explicit stack or queue, we see that the time complexity remains O(n), and the space complexity O(h). An iterative preorder traversal, which also uses an explicit stack, would have the same time and space complexities as the recursive approach. However, the recursive method is often preferred for its simplicity and elegance, as it avoids explicit stack management. Finally, let's summarize this with a mathematical proof of the time and space complexities. For time complexity, each node in the binary tree is visited exactly once, and each visit involves a constant time operation, O(1). With n nodes in the tree, the total time complexity becomes O(n)*(O)(1), which simplifies to O(n). For space complexity, the depth of the recursion stack is determined by the height of the tree, h. In the worst-case scenario, where the tree is skewed, the height is equal to n, resulting in a space complexity of O, n. In the best-case scenario, where the tree is perfectly balanced, the height is log n, leading to a space complexity of O, log n. Thus, the overall time complexity is O, n, and the space complexity is O, h, where h represents the height of the binary tree. When working on binary tree preorder traversal, there are several common mistakes to watch out for. First, it's easy to confuse traversal orders. Remember, in preorder traversal, we process the current node first, followed by the left subtree, and then the right subtree. Mixing this up with inorder or postorder traversals will lead to incorrect results, so always double-check the order before writing your code. Another issue is forgetting to handle null nodes in recursive solutions. This can cause runtime errors, so it's critical to include a base case that checks for null input. For iterative solutions, mismanaging the stack is a frequent pitfall. Keep in mind that the stack operates as a last-in first-out structure, so the right child must be pushed onto the stack before the left child to maintain the correct traversal order. Additionally, watch out for inefficient string concatenation inside loops, as strings are immutable in Python. Instead, use a list to accumulate results and join them afterward for better performance. Lastly, if you're using shared state like a global list in recursive solutions, ensure you reset it between test cases. Forgetting this can lead to incorrect results when running multiple test cases back to back. Now, let's focus on some key interview insights to help you excel in problem solving. Understanding the problem statement thoroughly is essential. Interviewers may ask you to adapt preorder traversal to specific applications, like serializing a tree, so be ready to explain the traversal order and adjust your solution. It's also important to be proficient with both iterative and recursive approaches. Recursive solutions demonstrate your understanding of recursion and base cases, while iterative solutions showcase your ability to use stacks effectively. Additionally, handling edge cases is crucial. Be prepared for scenarios like an empty tree, a single node, or highly unbalanced trees where all nodes are on one side. Space complexity is another topic interviewers may explore. For recursive solutions, the call stack uses O, H, space, where H is the tree's height. Iterative solutions also require O, H, space for the stack. Lastly, practicing related problems can deepen your understanding. For instance, LeetCode 94 focuses on inorder traversal, LeetCode 145 covers postorder, and LeetCode 102 introduces level order traversal. Exploring these problems will give you a well-rounded perspective. Finally, let's explore some alternative approaches and the trade-offs involved. The recursive approach is often preferred for its simplicity and intuitive nature. It's easy to implement and understand, but it does come with the drawback of using O, H, space for the call stack, which can lead to stack overflow in cases of very deep trees. The iterative approach, on the other hand, avoids recursion-related issues by using an explicit stack. This provides more control over the traversal process, but it can be slightly more complex to implement and requires careful attention to the order in which nodes are pushed and popped from the stack. Another option is Morris traversal, which is unique in that it uses O1 space by temporarily modifying the tree structure during traversal. While this method is highly space efficient, it can be less intuitive and harder to debug due to the temporary changes made to the tree. Each approach has its strengths and weaknesses, so your choice should depend on the problem requirements and constraints. Great job! To summarize, we tackled preorder traversal using both recursive and iterative approaches, with key insights into their time and space complexities. Remember, mastering tree traversal is essential for understanding tree-based problems in coding interviews. Thanks for tuning in, and don't forget to like, comment, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!